Title: What Happens When Physics Breaks?
A cinematic space documentary written and directed by Saiyari.A.
What if everything that has mass gets it from something you can't see? Something that fills the entire universe. Beneath everything you see lies a hidden world of interactions. In physics, there are particles that do not build matter. They carry forces. They are called bosons. Fermions make matter. Bosons make things happen. 4 fundamental forces govern the universe, each carried by a boson. But there was a problem. Why do some particles have mass, while others do not? In the 1960s, Peter Higgs proposed a radical idea: an invisible field, present everywhere. Some particles interact with it and gain mass. The more they interact, the heavier they become. To prove this idea, scientists built the most powerful machine ever created. Deep beneath the Earth, the Large Hadron Collider. In 2012, after decades of searching, they found it. The media called it the God particle, a powerful name, mysterious, almost sacred. But science does not speak this language. The name came from a book by Leon Lederman. Originally, it was called the goddamn particle, the damned particle, because it was so difficult to find. Physicists like François Englert remind us, this name is misleading. Its real name is simple, the Higgs boson.
Particle physicist David J. Miller compared the Higgs boson and the Higgs mechanism to a party gathering of political party members. The Higgs field is likened to a group of people initially occupying a living room in a uniform manner. When a well-known political figure enters the room, they attract supporters, giving them significant mass. This gathering corresponds to the Higgs mechanism, which assigns mass to particles. It is not the boson that directly confers mass to particles. The boson is a manifestation of the Higgs field and the Higgs mechanism, which in turn give mass to particles. In this metaphor, one can compare this to the following phenomenon: someone outside, in the hallway, spreading a rumor to the people near the door. A crowd of activists forms in the same way and spreads, like a wave, throughout the room to transmit the information. This crowd corresponds to the Higgs boson. The observation of the Higgs boson would therefore constitute a very strong indication of the existence of the Higgs mechanism. But this mechanism could exist even if the boson itself did not exist.
It does not answer everything, but it changes everything. We do not live in a universe made of matter, but in a universe of relationships, and bosons are the language of reality. The Higgs boson doesn't change our daily lives, but it does change our understanding of reality. The idea of post-Higgs physics is not pure fantasy, but neither is it a magic bullet for instant technological breakthroughs. In reality, if deviations from the standard model of particle physics emerge thanks to more precise measurements of the Higgs boson or new experiments, we will be faced with scenarios ranging from simple adjustments to a complete overhaul of the laws of physics.
Future scenarios, 5 to 10 years and beyond, with approximate and naturally uncertain probability estimates.
Scenario 1. Minor deviations within the current framework. Approximate probability, 45%. The idea: more precise measurements of the Higgs boson's coupling constants reveal small discrepancies from predictions. What does this mean? The existence of heavier particles exerting virtual effects. Updated calculations, no model collapse. Impact: scientific, significant, improvement in accuracy. Technical, indirect quantum mechanics subsequently led to electronics. Conclusion: sometimes the laws don't change. We simply discover that they are more precise than we imagined.
Scenario 2. A gateway to dark matter. Probability, 25%. The idea: the Higgs boson acts as a portal between ordinary matter and a dark sector. What will we see? Unexpected decays of the Higgs boson energy loss in collisions. Impact: understanding dark matter, one of the universe's greatest mysteries. impacts on cosmology, and potentially new detection techniques.
Scenario 3. There are multiple Higgs fields. Probability, 15% idea. Instead of a single field, there are multiple fields. This implies multiple Higgs bosons. Possible theoretical framework, models such as supersymmetry and SUSY. Consequences, a more complex world, deeper symmetry in nature. Impact, 1. Theoretical revolution. 2. Large-scale applications.
Scenario 4. Partial collapse of the Standard Model. Probability, 10% theory. Experiments reveal results that are inexplicable within the framework of the Standard Model of particle physics. Consequences, 1. Entirely new physics. 2. The possible emergence of additional forces or new dimensions. Impact, like the revolution of general relativity, but practical applications will take decades.
Scenario 5. Unexpected physics probability. 5% idea, a phenomenon that doesn't fit any current model. Possible example, a change in the properties of space itself. Discovery of a new field of physics. Impact, 1. Redefinition of the concept of reality. 2. Unexpected applications, as was historically the case with electricity and quantum mechanics.
Strategic summary. Most frequent scenario, gradual cognitive evolution. Low percentage, technological disruption. The technological impact is always delayed 10 to 50 years. A powerful vision. The discovery of the Higgs boson was not an end in itself. It provided the first evidence that what we cannot see may be more complex than we think.
Research centers don't exploit a discovery like the Higgs boson quickly or directly. The path is long and fraught with uncertainty. What actually happens is a systematic, phased process of transforming fundamental knowledge into scientific, then technological, and sometimes economic value over years or decades.
How do they think?
1. From discovery to verifiable questions. Central question. Are there any deviations from the standard model of particle physics? Methods. More precise measurement of the coupling constants of the Higgs boson. Searching for rare decays. Comparison of results with other models. OOTLs. CERN. Interstellar Hadron Language and its updates. Objective. To identify any potential limitations of the model.
2. Build research portfolios rather than betting randomly. We don't bet on a single idea. The search ports are made up of program Higgs boson precision, high precision measurements, dark sector program potential gateways to dark matter, new physics program, models beyond the current framework. Objective, to reduce scientific risks by diversifying approaches.
3. Design experiments before obtaining results. The paradox? Experiments are designed even before we know what we're going to discover. How? Identify potential signals. Fermas. Build detectors capable of detecting them. Develop advanced data analysis tools. Objective, to not miss any rare phenomena.
4. Invest in intermediate technologies. Even if new physical phenomena don't emerge immediately, resources are invested in technologies that support research. More sensitive detectors, massive computing and data analysis, innovative particle acceleration. Historically, such investments have led to unexpected applications. The web, imaging technologies, etc. Objective, to obtain a return on technological investment even without a major discovery.
5. Transforming results into a knowledge system. The results don't remain confined to the laboratory. Open publication plus international collaboration. Linking physics to cosmology. Integrating the results of other experiments. Objective, to build a unified picture of reality.
6. Long-term vision, 10 to 30 years. The question isn't, what will we gain now? But, what could open doors later? Here's the answer. Could the properties of the Higgs field reveal a different vacuum energy? Are there hidden sectors associated with it? Objective: to sow the seeds of future revolutions.
7. Red team thinking, counter-thinking. Within some programs offer a critical approach. What if our signals were just noise? What if our interpretation was wrong? How can our hypothesis be quickly refuted? Objective: to avoid scientific illusions.
8. Where does the real exploitation lie? Not in the particle itself, but in the tools, dot detectors, computing, the methodologies, data science, simulations, the networks, collaboration, open science. In other words, value is realized indirectly, a realistic conclusion. There is no magic bullet for transforming Higgs boson physics into technology tomorrow. There is a whole system that transforms discovery into knowledge, which involves tools, which involves applications.
General conclusion. Science doesn't exploit discoveries. Rather, it builds entire universes of questions around them. And from these questions, the technologies that change the world are born.
The Higgs sector was never the end of physics. It was the beginning of a deeper unknown.
In post-physics, the goal is no longer to discover laws, but to survive their instability.
Are we observing new physics, or the limits of our current understanding collapsing?
We once asked what the universe is made of. Now we ask whether it remains consistent long enough to study.
By 2040, physics will no longer be expanding. It will fragment.
The Higgs sector does not yet alter operational reality, but it defines the next frontier of physical understanding.
The Higgs sector does not yet alter operational reality, but it defines the next frontier of physical understanding.
In strategic terms, we are not exploiting the Higgs discovery. We are mapping the unknown structures it may reveal.
2026, Saiyari.A. All rights reserved.